Should I start?
Yeah, please do.
So, good evening, everyone. My topic for this presentation is SU3 and particles.
Oh, by the way, can anybody? Yeah, okay, fine. Sorry, I just couldn't hear you a while. I can now.
Okay.
My earphone had come loose.
Oh, all right. So, my topic is SU3 and particle physics. And first, I will talk about what is SU3. And SU3 is a eight-dimensional simple Lie group with the group operation of matrix multiplication. Its elements are represented in this manner, which basically means it comprises of all 3 cross 3 invertible matrices which satisfy the property which are unitary and have determinant 1. SU3 plays a very important role in particle physics, particularly for the formulation of the quark model and in quantum chromodynamics, which is the theory of strong interactions. Now, first, we'll look at SU3 Lie algebra, and uh, we can see that the generators of the Lie algebra in the defining of fundamental representation are given in this way. Then TA equals lambda A by 2, where lambda A are the German matrices, which are given here. These basically span all traceless Hermitian matrices, which are the requirements for the generators. The traceless requirements comes from the unitary requirement, and we'll find this as each a general element of the group can be represented as exponential of I times a linear combination of the generators, which gives us that these generators must be traceless. These generators are found to satisfy this commutation relation, and where the ABCs are structure constants of the Lie algebra. And this is quite similar to what we saw in class for the SU2 case, where the generators were given by Pauli matrices. In class, we had represented them by as Ji equals sigma I by 2. I've written II and I'll explain. And this soon become clear why I've done this. And these follow the commutation rule as given here, where instead of structure constants, we just have the Levi-Civita tensors, and these are the Pauli matrices. Um, so before I talk about SU3, how SU3 applies in particle physics, I want to talk about SU2. And we have already seen how SU2 plays a role in spin states, and uh, a similar symmetry exists in particle physics, which is known as isospin. So, what is isospin? Historically, when the neutron was first discovered, it was suggested that the neutron and the proton are to be regarded as two states of the single particle on the basis of their similar masses. And uh, in a similar way as to the spin up and spin down states of a spin off system. And isospin was formulated to it was said that isospin symmetry governed and isospin symmetry was an SU2 symmetry which governed rotation of P and N into each other. Now, similar to as you have done in class for the J case, here, firstly, we see that none of the I1, I2, I3 commute with each other. So we can generate the Cartan subalgebra similar to as you have considered J3. Here we consider I3, which becomes our generator for the Cartan subalgebra. And we recast I1 and I2 in this manner, I plus minus, which are known as the shifting operators, as I1 plus minus I2. And we find that the commutator of I3 with I plus and I minus can be written in this manner, and this basically implies that I plus and I minus are eigenstates of adjoint I3 with eigenvalues plus 1 and minus 1. Now, similar to as we have found J and M, we can have isospin states in this manner, I and I3, where I3 are in here. I3 represent the eigenvalues of I3, and I is the highest such, is the maximum value of the I3. And the shifting operators are found to act on these states in this manner. And they basically I plus changes the I3 value by 1, I minus is found to change the I3 by reduce the I3 value by 1. Now, as I was talking about P and N, they they are expected to form an isospin doublet, uh, known as the nucleon state, represented thus, which gives us the basis in this manner, P10 and n equals to 0, 1. And from this, we can clearly say that the isospin states are represented at this way, P as half half and n as half and minus half. Now, as I was talking about the isospin symmetry, here is clear to say that I plus and y I plus and I minus are known as the shifting operators. So I minus acting on the p state gives us n, and I plus acting on the n state gives us p, which is basically how we define the isospin symmetry in this case. However, what we'll be talking about more importantly is the quark model. And in the context of the quark model, it's actually the up and down quarks which are uh, considered to form an isospin doublet with U as half half and D as half minus half. And any other isomultiplets, including the proton and neutron, which in the context of the quark model are considered to be made up of quarks, can be found, uh, are made up of uh, combinations of these quarks. No, okay, this is wrong. This is more quarks, but yeah. Um, so another important point to note is that isospin symmetry is not an exact symmetry, which implies that it's not unconditionally valid. It's a good approximate symmetry, and uh, it's a good approximate symmetry because of the closeness of masses of P and M, but again, it's not exact. And now we'll see that it actually is a part of a larger, more approximate symmetry, which plays an important role in classifying observed particle families. And what is the symmetry? This is known as flavor symmetry. Now, after isospin, at some point it was found that some particles existed which were produced through strong interactions, but decayed only through weak interactions. An example of this is the positively charged kaon, K plus. And this motivated addition of a concept of strangeness quantum number by Gell-Mann and Nishijima. And uh, to add this to the isospin, to generalize the isospin symmetry, it became necessary to add another component and represent the three quarks in this manner. And these were known as the different flavors of quarks. And we'll see that they have an underlying SU3 symmetry, which led to development of the quark model. Firstly, again, going back to the algebra of the SU3 group, from the commutation relation, we can see that the two generators T3 and T8 commute with each other's. And here in this case, this implies that they generate the Cartan subalgebra. Here, since the two elements generate the Cartan subalgebra, we call the SU3 as a rank 2 algebra, unlike SU2, which was a rank 1 algebra. Now, for context of particle physics, we actually use the standard form or the Cartan rail form of the generators, which would give us the important results. In this way, we recast the T1 and T2 to give us the shifting operators t plus and t minus, t4 and t5 to give us v plus and v minus. We label it as v plus and v minus, and t6 and t7 as u plus u minus, and t8 we write as y. We cast t8 as y. Now, let's look at the commutators with different commutators involved here. With T3, we find T3 with T plus T minus gives us plus minus T plus minus, which implies that T plus minus are eigenstates of adjoint of T3 with eigenvalues plus 1 and minus 1. Similarly, U plus and U minus are also the same, and with eigenvalues minus plus half. Similarly for T3 and V plus V minus, and again, similarly, commutators, we can look at commutators of Y, and again, T plus T minus are eigenvectors of adjoint Y with eigenvalue 0, and U plus U minus are of adjoint of Y with plus minus 1, and similarly for these. We also look at commutators among the shifting operators or the ladder operators. T plus and T minus gives us T3. U plus and U minus gives us 3 by 2 y minus T3, and V plus and V minus gives us 3 by 2 y plus T3. Now, using the same notation as we have done in class, we take H1 as T3 and H2 as Y, which are the generators of the Cartan subalgebra, and we have the U100, D010, and S001, which are simultaneous eigenstates of H1 and H2. And again, as you have seen, T3 and T8 commute, so do H1 and H2, and this gives us the commutator between them as 0. These are the explicit forms for the H1 and H2. Now, to find the weights, we basically find the eigenvalues corresponding to H1 and H2. mu1 corresponds to H1 and mu2 corresponds to H2. For the U state, we find that this eigenvalue corresponding to H1, and this is the eigenvalue corresponding to uh, H2. So similarly for D and S, and these are the weights for the three different states, quark states. Uh, Now, from the commutators, we can find the different roots. As we have seen here, adjoint of T3 and T plus will give us plus. The adjoint of T3 times T plus gives us plus of T plus 1 on in times T plus, and this gives, and similarly adjoint of Y times T plus gives 0 times T plus, and this gives us the first root 1 0. Taking the conjugate, that's a negative 1, will give us the basically the negative of that, that's minus of alpha 1 vector. And so similarly, we can do this for T3 with U plus and V plus, T3 U plus and Y U plus, and T3 V plus and Y V plus, and this gives us uh, alpha 2 vector and alpha 3 vector, and taking the minus ones, U minus and V minus, this will give us basically the minus alpha 2 vector and minus alpha 3 vector. Now, so uh, we can relate the shifting operators to each of the roots in this manner. E alpha 1 basically corresponds to T plus, and E alpha 2 to U plus, and E alpha 3 to V plus. And similarly for the conjugates, E minus alpha 1 to T minus, E minus alpha 2 to U minus, and E minus alpha 3 to V minus. And so another thing we can notice is from the commutators of the shifting operators themselves, which are here, say T plus and T minus gives us T3, and this basically implies E alpha 1, and E minus alpha 1 gives us T3. And again, we also found that T3 with T plus minus gives us again T plus minus only. And this implies that the commutator between E alpha 1, E minus alpha 1, E alpha 1, E minus alpha 1 forms a closed SU2 subalgebra. In fact, uh, this is the same thing as the SU2 isospin case, and and thus this implies that the isospin symmetry is a part of the flavor symmetry. We can see this from the generators themselves as well. Now, here you can see the generators lambda 1, 0, 1, 1, 0, and rest are 0, 0 minus I 0, rest are 0, lambda 3 like this, and comparing this with the sigma 1, we can see that they all carry near the same structure. So, and similarly, we can say this for the case involving alpha 2 and alpha 3 as well. In this case, what we do is we take E alpha to U plus and E minus alpha to U minus, and this is our commutator. And when you take the commutator of this with the U plus and U minus, again we find using these two, again we find that we'll get those corresponding states only with some factors. And again, this would imply the same thing for alpha 2 and alpha 3, that is for U and V, which implies that this is the for the isospin case, and similarly would have U plus U minus, the commutator between them, and U plus and U minus would form another closed SU2 subalgebra, and V plus commutator between V plus and V minus, V plus and V minus would form another SU2 subalgebra. And these are sometimes referred to as the U spin and V spin cases. And so our SU2 algebra can be broken down into these three SU2 subalgebras. Does anyone have any doubts till this point? Okay, so I'll proceed. Uh, Now, how this comes into... Can everyone hear me?
Yeah, I can hear you, but sometimes it's
Okay.
sort of breaking up. Is that the case for everybody, or is it me only?
No, sir, it's not breaking up for me.
No, it's not really breaking up. It's just stuttering a bit from time to time for me.
Yes, sir, even for me.
Um,
It's not exactly a breakup, but anyway, that's okay. We can make out what you're saying.
okay. So now I've talked about the SU3 algebra, and now I'll talk about how this exactly applies to the quark model in particular, and how this flavor symmetry applies, how we formulate the flavor symmetry. Because of the commutator between T3 and T8, I would again, instead of using this notation, I would again go back to the notations, these notations which I have written here, because uh, I was more comfortable using them. And now, because of the commutator between T3 and T8, this allows us to label various states as in this way: T3, where T3 are the T3 eigenvalues and Y are the Y eigenvalues. T3, as we have already shown, corresponds to the isospin only, and Y is referred to as the hypercharge. Now, the shifting operators act on this state in the manner as shown in this figure. The T plus acts only on the T3 values and increases T plus acts increases the T3 value by 1, T minus decreases it by 1, V plus increases the T3 value by half and the Y value by 1, while V minus does the opposite. U plus decreases the T3 value by half and increases the Y value by 1 and U minus does the opposite. And so now, uh, as per this labeling, the up, down, and strange quarks can just be represented in this manner, and these basically correspond to the weights as I've said before. The weights are the eigenvalues, and so these are also basically the eigenvalues, and we can write the up, down, and strange quarks in this manner. Now, the diagrammat and this gives us the fundamental quark representation 3 and the fundamental anti-quark representation 3 bar, which diagrammatically in the y y t3 plane are represented in this manner, as we can see from the t3 and y values also. This is the quark multi triplet, and this is fundamental quark triplet, and this is the fundamental anti-quark triplet. Now, why exactly is this important? This actually allows us to talk about what combinations of these quarks would look like, and mm, it, combinations of these quarks gives us a plethora of particles to talk about, and uh, the those those are the particles which are predicted by this quark model. So one such class of particles are mesons. Mesons are bound states between a quark and an anti-quark, and for the three different flavors of quarks which we have seen, U, D, and S, we can say that there are 9 possible combinations, and these are got by taking the direct product of the fundamental triplet representation and the fundamental uh, the quark triplet representation and anti-quark triplet representation. So the simplest way to go about doing this is diagrammatically in the T3Y plane, where we just superimpose the anti-quark triplet over each flavor of the quark triplet, and this gives us the following corresponding diagram, where this line corresponds to y equals to plus 1, this corresponds to y equals to minus 1, this is y equals to 0, and this corresponds to T3 as minus half, T3 as half, T3 1, and this corresponds to T3 as minus 1. And uh, the uh, this also gives us the here we can see it gives us three states A, B, and C, which have both the eigenvalues equals to 0. The state A is written in this manner, and it is considered to be a part of an isospin triplet with du bar and ud bar in this manner, and we can use as we have seen the action of t plus and t minus. But before I talk about the action of that in here, uh, I forgot to mention this. Here from these diagrams, it's clear to see that we can use uh, t plus changes d to u and t minus changes u to d. Similarly, v plus can change s to u, and u plus can change s to d, and accordingly the other ones act in that manner, and can this shows us a symmetry between the flavor symmetry between these quarks. Now, in this context, as I was talking, A is considered to be part of this isospin triplet, and again, T plus and T minus can be used to transform between one and the other. The state B is considered to be an isospin singlet, and it's written in this manner, while the state C is written in this manner, and it's a unitary singlet which is separate from this octet. Now, this octet is known as the meson octet, and it predicts that the various mesons exist as two isospin doublets, one with y equals to +1, one with y equals to -1, an isospin triplet, and singlet with y equals to 0, and this unitary singlet C. Now, clearly diagrammatically, we can see that the direct product decomposes as uh, 8 plus 1, which is what Sharika also showed yesterday, which is consistent with what Sharika showed yesterday using the Young tableaus too. Now, in a similar manner, we can superimpose the quark triplet over the quark triplets flavors of the quark triplet itself, and this would give us a decomposition in this manner, direct sum of 6 and 3 bar. And then if we take another and then if we superimpose another quark triplet, we'd get the final decomposition in this manner: 10 plus 8 plus 8 plus 1. And this basically corresponds to the baryon octet 8, which is written here. And as you can see, the P and N also form a part of this, and the baryon decuplet, which is found to be this. Now, this was the basically the eightfold way, which was postulated by Gell-Mann and Neyman, and all these different particles hadrons were predicted, the mesons and the baryons. Now, this was very useful because some particles say like omega minus here wasn't discovered by that time, but it was predicted by this model, and when omega minus was finally discovered, it validated the quark model and hence its underlying symmetry as well. Now, however, there are certain problems with this flavor symmetry. Again, like isospin, it's not an exact symmetry. If it were an exact symmetry, then for one, the up, down, and strange quarks should have similar masses. But it is found that the strange quark is heavier than the up and the down quarks, and this is also the case for various mesons and baryons, where ones belonging to the same multiplet do not are found not to have the same masses. So firstly, the flavor symmetry is not an exact symmetry, and secondly, if you look at the wave functions of the states, for example, say the delta plus plus state, which is a UUU case here given here, it was found that the wave function was completely symmetric, uh, and this this violated the Pauli's principle, and so too this couldn't be the case. And so to take care of this problem, an extra degree of freedom was added, which is known as color. And uh, so the extra degree of freedom for quarks was added, which was known as color, and color is also applies as a SU3 symmetry. Now, mm, each quark is assumed to have three possible colors: red, green, and blue. And because these are colors associated to the same quark, there's the it's basically the same mass, and this means that the SU3 color symmetry is an exact symmetry. And in this case, the fundamental triplet representation corresponds to the colors themselves. I mean, the quarks of these colors, which is represented in this manner. Now, in nature, it's found that uh, the hadrons are found to be colorless, and so this implies that the constituents of hadrons, which are the quarks and antiquarks, have colors in such a manner such that their combination is colorless. In case of the mesons, they are made up of basically a quark and an antiquark, and so the quark would have some color and the antiquark would have the complementary color of that color to give us a colorless hadron. In the case of baryons, say for example, if all the three colors are present for the three quarks or the three antiquarks, R, G, B, then or R bar, G bar, B bar, then it will give us a colorless hadron. Now, for this state RGB, it's found under an SU3 transformation. We can say that it transform in this manner. Psi of x goes to psi prime x exponential. This is general way of writing any SU3 as I mentioned at the beginning. Exponential minus I ta theta a psi x. Now, here, if the theta a, which are the parameters, do not depend on the space-time, then such a transformation is a global symmetry of the Dirac Lagrangian is found to be a global symmetry for the Dirac Lagrangian for quarks. However, if the symmetry is local and the theta a depend on the x, then we need the Dirac Lagrangian needs to be modified by introducing the covariant derivative, and this requires us to introduce 8 vector bosons which correspond to the 8 generators, and this is a requirement to implement this color symmetry in the Dirac Lagrangian for quarks. Now these 8 vector bosons are known as gluons, and so now again, as this is also an SU3 symmetry. It's the structure of it is exactly similar to the one we have discussed for the flavor one. And so represent the gluons, we need possible combinations of the colors. And one possible representation is directly given in analogy to the meson octet. And as you can see, the meson octet here, ds bar, us bar, ud bar, us bar, ds bar. So instead of ud and s, we take r, g, b, and this gives us uh, these 8 gluons, r, g bar, r, b bar, g, b bar, and these are exactly the same as the meson octet. And there's also the corresponding singlet state as we have written C here, RR, which will be root over 1 by 3 RR bar, DD bar, BB bar, but it actually, it's found that it cannot be a mediator for between color charges, because if it were, it would imply that strong interaction works between colorless hadrons has infinite range, which is definitely found not to be the case. And these gluons are important because in the theory of QCD, exchanges between these gluons mediates the strong interaction between quarks and basically forms the bedrock of the theory of strong interactions. And these are the references I used for my talk.
References, I can't see them. Can everybody? Yeah, I can see them now. Maybe some delay. Okay, anybody has any questions? Oh, first the applause, of course. Pretty well done. Now, questions? If nobody has any questions, I have one. Could you just explain the 3 cross 3 equals 6 plus 3 bar? The superposition of diagrams technique. Could you just explain how you got exactly 6 plus 3 bar? That way? Or, yeah, that was the one.
Drawn it, but
So when you take a triangle, and on all points you put triangles. Okay, you get basically 3 is a triangle, right? And when you're saying you're doing 3 cross
yeah,
3, you're putting triangles on all 3 points. In fact, this is I'm pretty sure most of you will be able to figure out that this will also work for addition of angular momentum. In fact, angular momentum is so easy to add that people don't really worry about these diagrammatic techniques all that much. At least not for 2 spins. But you could take the ladder of all spin eigenvalues, draw them on a line. Say you have spin 5, then on and say, let's say not spin 5, let's say 5, that means spin 2, and 3, let's say spin 1. So spin 2 will have 5 points on a line. On each of these points, you will draw those 3 points, and you'll go from there. So a total of 15 points. In this case, for 6 cross 3, you get a sorry, 3 cross 3, you get total of 9 points. That's fine. And this is more intricate, of course, basically because you're in 2 dimensions. So it looks like a nice pattern. The question I have for you is, how do you recognize that those 9 points make up a 6 and a 3?
um, so that'll basically give us I mean, diagrammatic.
Sorry, I can't hear you.
Huh.
Could you be
So
slower? Because
hello.
I'm getting some stutter. Yeah, I can.
Can you hear me now?
Yes, go
Okay.
ahead.
So here what we have done, we have superimposed the tree bar,
Mhm.
this tree bar over each of these ones like this. Now for the tree cross tree, we have to superimpose
Oh,
this
that's
one
fine. But
itself
now my question is, how do you know
over.
it's, say, for 3 cross 3 bar, you get 9 points.
Hmm,
So how do you know it's 8 plus 1?
yeah. I mean, there'll be a larger triangle here, and the smaller triangle here, which the smaller triangle corresponds to the basically the tree bar, and the larger upside down triangle which looks like this corresponds to the six. It will have an isospin triplet with y equals to 1 and isospin singleted y equals to -2 and an isospin doublet with y equals to -1. And then we have this tree bar.
Okay. Okay.
I mean, I would
Yeah,
love
it
to
would
have
have been
shown
better
it
if you could draw
diagrammatically,
it
but I'm
directly.
not
But of course, it's difficult to show that
exactly.
just on
But
the screen with a cursor. But I get your point. Okay. I know. It's
I mean,
dynamically showing this is
do I
much better than
copy now and
having to sort of wave your
yeah,
pointer on the screen.
exactly. I did it in my copy to show the
No, even
diagram,
that
but
would be
I'm not sure if
static. But so
I
you would
could
have to
show
show it step by step. It would be difficult. Anyway, I understand what you're saying. That's fine.
it.
Okay.
Okay.
Any other questions? And if not, is Ritik here? So are you prepared to start?
Yes, sir.
Yes. Okay.
Yes, sir.
Good.
Uh,
Yeah,
so
you should
should I
stop presenting, or
stop
he
presenting?
can start. It'll override anyway. Apart from the
Okay,
organizer, everybody else's
fine.
presentation can be overridden. Yeah,
Is my
somebody's
screen
screen is
visible?
visible. I'm assuming it's yours. Yeah, it is yours.
Oh, so is the first
Yeah,
this page
it
visible?
is.
Okay, so today my presentation is on conformal symmetry and how is it important, how is it a very important tool in modern physics, and some of its aspects of and some of the aspects of conformal groups. So first of all, when we talk about any symmetry in physics, symmetry transformation, what we mean is when we do that operation on the system, basically our physics remains invariant. Although our equations may be covariant, but the physics remains invariant. So to understand conformal symmetry better, we first have to define what is a conformal transformation. Like if we wanted to, when we understood Lorentz symmetry, we first defined Lorentz transformation. So we start with the conformal. What is a conformal transformation? 1 minute. So a conformal transformation is basically an invertible coordinate transformation under which the metric is rescaled by a local factor. So the
So
local factor is very important. Yeah.
can you show us
Yes,
one
sir.
at a time? That is one page at a time.
It was happening. Yes, it is now. Uh,
Okay. Anyway, just try blowing it up. Yeah. Otherwise, it's too small.
no, it was happening. I don't know what happened because I just
Okay,
tried
fine.
it. It
Anyway, I
was
can
showing one
see
at a
it
time.
quite clearly
Is
now.
this fine?
That's fine
Oh,
for me.
okay. So yeah. So so when we do this coordinate transformation, the metric should scale by a local factor, and this local factor is a very important thing here because this factor is can be dependent on the point. It shouldn't be a constant. And another condition is that this should be greater than zero. So what we want to find is all such transformations which adhere to this rule. So to do that, another important point is that if we can observe that if we set this lambda x equal to 1 for a coordinate transformation which transforms in a way which leaves the metric invariant, we get a Poincare group. We'll get basically Poincare transformations which are isometries of our space time. So basically, we can already see that for a specific case from conformal transformation, we can recover our Poincare transformations. And as lambda x is dependent on is a function of that, we can see that this encompasses a greater amount of transformations. So another important point is that, which we can see, conformal transformations preserves angles but not distances. So we can imagine conformal transformations as stretching or dilating things, but the angle between two lines, if we can say so, it remains the same. So to to move ahead, we define an infinitesimal transformation of the form. Here the primes are mixed up. It should be x prime mu, sorry, it should be x prime mu, which goes as x mu plus epsilon mu, which is some function of the space-time coordinates. So under such a transformation, the metric changes as follows. So this can be easily computed. So g mu nu goes to g mu nu minus del mu e nu epsilon nu plus del nu epsilon mu. And here I am only taking the up to first order because it's an infinitesimal transformation. So the requirement that transformation be conformal, which is the metric should be scaled by a local factor, that gives us that this del mu epsilon nu plus del nu epsilon mu should be some fx times g mu nu, where fx is some function that we have to determine. And now the factor fx can be determined from this equation by contracting both sides with g mu nu. So if we do that, we get fx is equal to 2 by d del rho epsilon rho. And the point to note is d is the dimension of the space time. And then we have to manipulate these equations to get more information out of them. So we can apply an extra derivative of del rho on equation 1, and then we can permute all the three indices to get three equations, and then we add two of them and subtract the third. So we end up with this relation. So again, we contract the previous equation with its g mu nu, and we end up with 2 del square epsilon mu is equal to 2 minus d del mu f. So this is another equation, and we can get two more equations out of this. We can apply del mu on this expression and del square on the first equation to get this relation. And finally, we can contract this equation with eta mu nu to get the last equation. So the main point of these equations is that these equations impose some kind of constraint on what f can be, and from that f what that coordinate transformation can be. So, but we see that these equations have an explicit dependence on the space-time dimension. So that plays a very important role here. For example, if I consider focus on equation 5, so in equation 5 I see there is a factor of 2 minus d. So if I have a space-time dimension of 2, so this left hand side goes to 0 and we won't get the sixth equation. So we can already see that d equal to 2 is some kind of a peculiarity here. And same for d equal to 1. For d equal to 1, this thing that if d is not equal to 1, then del square f is equal to 0. But if I put d equal to 1, then del square f can be anything. So these so 2 and 1 are sort of different cases. We can deal with one easily. D equal to 1 can be easily visualized because there is no constraint on the transformation. It just has to be a smooth transformation. All transformations are allowed because in one space-time dimension there is no concept of an angle. But for two-dimensional space-time, things are a little different, and I won't talk about it. The following presentation is on the dimensions d greater than equal to 3. So we have all these equations with us. So equations 5 and 6, del square f is equal to 0 for d greater than equal to 3. So if I put that in equation 5, it implies that del nu f is equal to 0. So that implies that the function f is at most linear in the space-time coordinates. So I can expand fx as a plus b mu x mu, where a and b mu are some constants. And if we use this expression in equation 3, we see that the long equation that del nu epsilon rho is a constant, which means that epsilon mu, the change in coordinates, is at most quadratic in the coordinates. So in a general form, I can expand epsilon mu as a mu plus b mu nu x nu plus c mu nu rho x nu x rho, where the coefficient the c mu nu rho is symmetric in the last two coefficients because x nu and x rho, this is just multiplication, they commute. So this is symmetric in the last two indices. Now, as epsilon mu in general follows the constraint that we have derived it from, each individual parts also obey those constraints. So we can look at individual parts of these equations time by time. So first, we treat the term a mu, and a mu is an infinitesimal translation we can easily see. So this thing is sorted out. And now to look at the linear term, we substitute the linear term in the original equation, which gave us the change in the metric, and we substitute it to get this b mu nu plus b nu mu is equal to 2 by d b lambda lambda eta mu nu. So what this equation says is that if we can decompose b mu nu into a symmetric and antisymmetric part. So this equation says that the symmetric part of b mu nu is a pure trace, and then we have the antisymmetric part. A pure trace here represents an infinitesimal scale transformation. Scale transformation basically just scales the coordinate. My coordinates x mu goes to lambda x mu. Whereas the antisymmetric part, as we know, antisymmetric infinitesimal transformation, this gives it a Lorentz transformation. So still now we haven't discovered anything sort of new. Like we already knew Lorentz transformations, we knew translations, we have an idea of scale transformations. So what is new about the conformal transformations? So now we look at the quadratic term. So substituting the quadratic term in equation 3 gives us this, the value of this coefficient. And the corresponding infinitesimal transformation is this: x prime mu is equal to x mu plus 2 times b dot. Here b dot x is basically x mu b mu contracted. I have written as x dot b, x mu minus b mu x square. So in the end, we see this is the only new kind. It's the only new thing we have got. So we should explore this thing more. What is this? What is this transformation and what does it mean? So this transformation bears the name of special conformal transformation. And from these infinitesimal transformations, we can generate the finite transformations. So translation is x mu plus a mu, dilation is alpha x mu, and this is the Lorentz transformation. And the SCT can be, this is the infinitesimal form. SCT can easily be derived from this. A quick way to check this is, if this is a finite transformation and suppose B is very small, so we can use the binomial expansion in the denominator, and expand it to easily recover the previous infinitesimal transformation that we derived. So first three transformations are familiar. The last one is new. And as I said, the conformal transformations, the trademark of them is they scale the metric by a local factor. So for the SCT, the associated local factor is given by this: lambda x is equal to 1 minus 2 b dot x, b square x square whole squared. To get a more intuitive understanding of SCT, we can define transformations which are known as inversion of the following form: x mu goes to x mu by x squared. So the SCT in the previous form, in the previous page that I wrote, can also be written down in the form x mu by x mu square is equal to x mu x square minus v mu. So we can easily see from the definition of inversions that SCT can be viewed as a translation preceded and followed by an inversion. Now we have, does anyone have any questions till now? Or am I going too fast or too slow?
I don't know. I know this stuff, but I'm not sure about the others. Ask them.
I am asking, I am asking, obviously I'm asking them.
No,
So
no.
does anyone
I don't know
have any
everything
doubt?
about this, but I know
Uh,
this particular thing.
Maybe could you go a little slower, slightly slower, not much.
Okay. So, but do you have any doubt that you want me to explain again some stuff?
No.
Okay. What we have done till now is we have found the form of the conformal transformations. Now, when we have a transformation, we would like to write the generators of those transformations. First, we digress into how do you define generators of any, be it any transformation. So for a coordinate transformation, that is parameter epsilon a, del mu is equal to x mu plus epsilon a, and del x mu by del epsilon a, and the corresponding field which transforms in the following way, where f, the functional derivative of thing which is taken, f is where phi prime x prime is equal to f of phi x. The convention we follow is that generator GA of a transformation of an action is defined in the following way: phi prime x minus phi x is equal to minus I epsilon a GA phi x. So from the above two equations, we can see that the generator can be written as phi is equal to del x mu del epsilon a del mu phi, where the functional derivative of the function is related to epsilon a's. So this is a general definition of a generator transformation. This can be used for anything. So using this definition, we are going to derive the generators of the conformal transformations we have written down before. But as all three of those transformations are familiar to us, the generators are already known. So that shouldn't be a big surprise. But the generator we are interested in is the generator of the special conformal transformation. So using the previous equation that we derived, we can write down the generators as follows. So the generator of translations is minus I times del mu. We know that the generator of dilations is minus I x mu del mu, and the generator of space-time rotations, this is also known to us I times I x mu del mu minus x nu del mu. But this is the new thing, the new transformation that we saw, the generator of this transformation. So now the next thing is to characterize are the commutation relations of these generators, which define the conformal algebra. Like in the case, like in the case of Lorentz group, the Lorentz generator defined the Lorentz algebra. So, so to define the conformal algebra, we note that the generators have the following commutation relationships. So these are the commutation relationships, and as we can see, the last equation, this is a familiar Lorentz algebra because this is a commutation relation between the rotations. So we will study the group by considering its associated algebra, the conformal algebra, which is the Lie algebra corresponding to the conformal group. So now how many generators does this group have? So that is very easy to count. Dilation has only one generator, the alpha times the thing which we scale with. Translations have D generators. Special conformal transformations are also characterized by a 4-vector B mu, so they also have D generators. And the Lorentz transformation we know have D into D minus 1 by 2 generators in D-dimensional space-time, because infinitesimal Lorentz transformations are characterized by omega mu nu, where it is an antisymmetric matrix. So in a D-dimensional space-time, it has D into D minus 1 by 2 elements. So if we add this up, we see we have total of half into D plus 1 into D plus 2 generators for the conformal algebra. Now, we already had these generators, but to put them in a more illuminating way, we can define alternate generators in the following way. J mu comma nu is equal to L mu nu. J minus 1 comma mu is equal to half P mu minus K mu. J 0 comma mu is equal to half P mu plus K mu. And J minus 1 comma 0 is the dilation operator. Where JAB, we can see where JAB is equal to minus JBA. J minus, it should be minus, this is wrong, it should be minus JBA. There's a mistake here. So we can check that these new generators obey the following commutation relationship. And this relationship should look very familiar to us, because that is the relationship we saw. Not the exact same thing, but this is the same type of relationship we saw for the Lorentz algebra. So this is something interesting here. So now to go further ahead, I have to specify in which space time I'm working. Is it Euclidean space time or it's a Minkowskian space time? So if I'm working in a Euclidean d-dimensional Euclidean space time, these generators obey SO d plus 1 comma 1 algebra. Uh, this is for the Euclidean space time. If I'm in a d-dimensional Minkowski space time, then these commutation relationships correspond to SO d comma 2 algebra. And if if for some reason, like if I have uh, p space indices and q time indices, where d is equal to p plus q, the conformal algebra corresponding to that will be SO p plus 1 comma q plus 1. So this is the basic, these are the basics of conformal algebra. Does anyone have any doubts till now? Okay, no, so I'll go ahead. So now, as in physics, we are mainly interested the representations representations of groups and how they act on different things. So we seek because till now, when we derived the equations, the relationships for the generators, the way in which we derive the generators, we made an assumption that the field phi x doesn't change under the action of conformal transformations. But if we have a multi-component field phi which has its own internal degrees of freedom, we have to get the complete generators. So to specify that, we'll have to know how that field transforms under a conformal transformation. So if we seek a representation Tg such that a multi-component field phi x transforms in the following way, where omega g are the parameters which tell us, which parameterize the conformal transformation. So when we saw we have to go ahead, we have to just study the Lorentz group a bit further. So when we derive the generators for the Lorentz group, the generator of space-time rotations were L mu nu, which were I times x mu del nu minus x nu del mu. But they were the generators for the fields which transform trivially under Lorentz transformation. So say if we have a field which doesn't transform trivially under a Lorentz transformation. So how do I So how do I get the full generators corresponding to that field? So we introduce a matrix representation S mu nu to define the infinitesimal action on the field at phi of 0. So the important thing is here is choosing the point 0 for now, because point 0 under a Lorentz transformation goes to space-time origin only. So that doesn't change. So we are seeking a representation of this form where L mu nu acting on this can be represented by a matrix S mu nu on the acting on the multi-component field. But now, as I have the translation operator with me, by the use of commutation relations, we can translate the generator L mu nu, which we only knew as S mu nu at space-time point 0, to a non-zero value. So how do we do that? Operate, we translate it using the translation operators using this formula, where L mu nu is sandwiched between E minus I x rho P rho and EI x rho P rho. So this can be easily simplified using the Baker-Hodder formula. I don't know if I'm saying the name correct, but I don't remember. But using that and using the commutation relations of the group, we can see that this comes out to be this S mu nu minus X nu P nu plus X nu P mu. So this allows us to write the action of generators on a multi-component field phi for Lorentz transformation as the following. This is the translation operator P mu phi, which is minus I del mu phi, and this is the space. These are the space-time rotation generators which act in the following way. S mu phi. This was the generator at space-time index, and this was the thing that we got on translating the generator to some other point x. Now to find the action of generators on the action of generators of the conformal group on some multi-component field phi, we do the same thing, but now as we know these two generators are already there in the conformal group, we worry about the other two generators, the generators of dilation and the generators of the special conformal transformations. So we denote S mu nu, this thing is already done, but still we denote S mu nu, delta tilde, and kappa nu to be the respective values of generator, L mu nu, the dilation operator, and K mu at x equal to 0. These must form a matrix representation of the algebra and follow the usual commutation relationships. And we do the same thing, we translate these operators to some other space-time point x to get the complete form. And when we do that, we get the following thing. The dilation operator, when it is translated from origin to some other point, it is delta tilde, the original form, plus minus x nu del nu. And the special conformal transformation operator, when translated, gives us this is a long expression, but basically this is the generator. This is a generator for the final form. Now, if the field phi x belongs to an irreducible representation of the Lorentz group, here I didn't write the commutation relationships which were used earlier. They are behind in the presentation, but I've written them again here. Basically, S mu nu is L mu nu, but at a specific point, and delta tilde is D dilation operator at a specific point. So this is the commutation relationship. So if phi x belongs to an irreducible representation of the Lorentz group, by Schur's lemma, delta tilde is a multiple of identity, as this commutator is 0. So delta tilde is some uh, constant times an identity matrix. But we also have the commutation relationship delta tilde comma kappa mu is equal to minus I kappa mu. So we conclude that all matrices K mu, because delta tilde is just an identity matrix times something. So the commutator of this thing should be 0. So we conclude that all matrices kappa mu vanish, and then delta tilde can be simply taken as a number, which is taken for some reason to be equal to minus I delta, where delta is a scaling dimension of the field. So what I mean by scaling dimension of the field phi, I'll return to that in a bit, but this is the name for delta. So now we have our full generators. So now we want to know how the field transforms. If we want to do any physics, we should know how a field transforms under a conformal transformation. So under a conformal transformation, x to x prime, we are taking a spinless field here for simplicity. A spinless field phi x transforms in the following manner. So as we can see, here this delta del x prime by del x mod, this is the Jacobian of the conformal transformation, and this is related to the scale factor in the following way. The scale factor is the thing by which the metric scales. So now, why do we call it the scaling dimension? So here we can see if we have a scale transformation, which is a type of a conformal transformation where each coordinate is just scaled by a factor of lambda. So this thing del x prime by del x, the Jacobian of the conformal transformation comes out to be lambda to the power d. So this d and d cancels, and we see that the field is simply multiplied by a factor of lambda to the power of minus delta. So that is the thing where the name of this delta is the scaling dimension is coming from. Under a specific type of conformal transformation, namely the scale transformation, this field transforms in a special way. Lambda to the power minus delta is just multiplied by the field. Does anyone have any doubts till now? Hello, am I audible?
You are. So
Okay,
I guess they have no doubts.
I don't know. Okay, okay.
Maybe
So now,
you're
like
going pretty well, but I'm not sure whether about the doubts. Or do you have a pact not to ask any questions?
not that I know of, sir.
Okay,
Okay.
go ahead.
So now, okay. So now we have talked about these purely mathematical things, conformal transformations, the generators. So what does this thing mean for the physics? So first, we all have dealt with in our courses of in QFT. We have dealt with relativistic quantum field theories. So that those are field theories which are invariant under the Poincare group. So those are the theories that we have dealt with. So what if those theories also had a conformal symmetry, namely that they remained invariant under a conformal transformation. So that is basically what a conformal field theory is. A conformal field theory is a quantum field theory that is invariant under the conformal group. So in addition to the symmetries of flat spacetime, the conformal field theories have extra spacetime symmetries that we have just discussed. And in practice, we will focus on theories with scale invariance, but that should seem odd because we have just claimed that the conformal transformations are a generalization of scaling in some sense. So the it is so to say a theory is conformally invariant by just saying that its scale invariant is wrong. Basically, it is wrong. But uh, so what are the differences between scale invariant and conformal invariant relativistic quantum field theories? So I don't have the proof of this statement, but it can be shown that scale invariance is enhanced to conformal invariance for d equal to 2 dimensions, and for d equal to 4 dimensions, there is a perturbative proof or enhancement, and there are no known examples of scale invariant, but not conformal field non-conformal field theories. So basically, what I'm saying here is that from now on, I will be using the terms conformally invariant, and scale invariant interchangeably. Ha. So so we have seen that scale invariance is a very big part of of conformal invariance. So when should we expect that a physical system should be scale invariance? A basic thing we should be able to see is that there should be no preferred length scale in the system. Because if I have a length scale, then obviously I cannot have any kind of scale invariance. That just goes opposite to that. So there is if there is a length scale, it prevents scale invariance for the system. For example, we can consider a simple system of two interacting electrons which are governed by the Coulomb potential. So the force between those two electrons just goes as 1 by r square, and basically the force depends on the distance between 2 points. And I know that distance between 2 points is invariant under a translation and a rotation. But if you want to demand extra symmetry, we can easily see that distance between 2 points is not preserved under a scale transformation, rather it is scaled by some factor. So we shouldn't have any type of length scale in the system. So an example of classical conformal field theory is the Maxwell theory in D equal to 4 dimensions, because photons have no mass. However, we can't just say that if a field theory is classically conformally invariant, we just can't hope to quantize it and say that it is also conformally invariant in a quantum sense. Because even though we can write down a Lagrangian with constant couplings, quantum mechanics introduces a dependence on energy scale, which we have seen in our QFT courses, which are called running coupling constants. So that basically has an explicit dependence on an energy scale. So, but we can talk about some quantum systems which are invariant, conformably invariant beyond the classical level. For example, we can talk about free massless quantized scalar field theory. It has no coupling parameters, it is massless and is therefore conformably invariant. Similarly, free massless fermions and free Maxwell fields have quantum conformal invariance. So this is quantum conformal invariance, but we can also see the usefulness of conformal field theories in critical phenomena that we have studied in our courses. So, for why is CFT used in statistical physics? So basically, CFT describes the critical points in statistical physics, the point at the end of a phase equilibrium where a continuous phase transition occurs. So, for 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 basically in a phase transition, basically we are talking here about second order phase transitions. The characteristic of a second order phase transition is that as we approach the critical point, the fluctuations increase, and they increase in such a way that the correlation length, which gives us how different degrees are correlated across a distance, they become so large that they diverge to infinity. So this divergence to infinity should give us a hint why conformal field theories become important at the critical point of a system. So this is just there for some reference. As we approach a critical point, the corresponding mass scale, uh, hmm, yeah, corresponding mass scale is vanishing because the correlation length goes to infinity. And these are some common things we use in statistical physics. The last relation, the scaling of the correlation function will be used in the next few slides, so you can have a look at it if you don't know the scaling form. But we'll see the usefulness of conformal field theory in computing this critical exponent eta, which is known as the anomalous dimension. So near a critical point, these quantities, the correlation length scales in the following way with some critical exponent. The specific heat capacity also does with some critical exponent. The susceptibility also does, and the magnetization also does. So these critical exponents are very important because they do not depend on the microscopic details of the system, but rather just on the symmetry and dimensionality of the system we are using. So
Uh,
basically, this is just a very hello,
uh,
yeah.
yeah. So, are you trying to uh, relate the scale invariance of CFT with statistical mechanics and CFT?
I am just trying to show where conformal field theory can be used in statistical physics, where the situation becomes apt, like where we can have scale invariance.
Okay. Okay.
So now this is a very simple demonstration of why CF conformal invariance can become very useful. So in the following section, we will see that just by demanding conformal invariance on a QFT, it is not strictly a QFT. We can say that for some statistical fields also, by just by demanding conformal invariance on a theory, we can explicitly derive to a constant the form of the 2 point correlation function without knowing anything about the action of the theory. So we have a 2 point correlation function. One thing I forgot to mention is that the scaling relation I describe for the fields like del x prime by del x to the power minus delta by d, that the fields which transform in that way are known as quasi-primary fields. So we have 2-point correlation function of quasi-primary fields here. So this is standard form for a correlation function. So one key assumption here is that the measure is conformally invariant. So this is a very key assumption. Now, if we are talking about a quantum theory, which we have quantized, so if the theory is conformally invariant at a classical level, the action should be invariant under a conformal transformation. So now what we are demanding is that under a conformal transformation, the system is invariant. So the correlation function should be after a transformation and before a transformation should be equal. So the correlation functions transform in the following way. These are just the transformation relations for the quasi-primary fields. You can see very easily that these are the same relations that I wrote down before. So the correlation functions transforms in the following way. Now we have what we are demanding is conformal symmetry. So scale invariance is a part of it. So we can just focus on a scale transform and say the same thing for a scale transformation. So if we have a 2-point correlation function and we demand and we try to see how it changes under a scale transformation. So this is, you can see it very easily. Here you put lambda to the power d, dd cancels. Here you put lambda to the power d, it cancels. And here we are assuming that both the fields have different scaling dimensions, delta 1 and delta 2. So under a scale transformation, this changes in the following way: phi1 x1, phi2 x2 is equal to lambda to the power delta 1 plus delta 2. Phi1 lambda x1, it should be x1, and phi2 lambda x2 here. They should be x1 and x2 here. And or as this is a relativistic quantum theory, we already have rotation and translation invariance. So that already gives some sort of constraint on the 2-point correlation function, namely that it should be a function of the distance between 2 points. So now we have two constraints, that this should be a function of distance between 2 points, and it has to follow this equation. So from that, we can easily see that if f is the form of the 2-point correlation function and x is the distance between 2 points, then fx should be equal to lambda to the power delta 1 plus delta 2 times f of lambda x due to scale invariance that we just described. So from that, we can easily see the 2-point correlation function should have the following form. It should be c by c, where it is some constant, divided by distance between the 2 points to the power delta 1 plus delta 2. So what we have seen here is that without even knowing the form of the action or any other thing about the theory, just by imposing symmetries, we have derived some sort of form of its 2-point correlation function. But but this is not complete yet, because we haven't still taken the special conformal transformation invariance under special conformal transformation into account. For such a transformation, the Jacobian of the transformation can be calculated as this thing, and the distance between 2 points and the invariance of correlation function implies the following thing. So this was a 2-point correlation function, and if I do a special conformal transformation on it, it changes to the following thing. And here I forgot to mention what are gamma 1 and gamma 2. Gamma 1 is, I don't it should be, gamma 1 should be, I think, 1 minus 2 b dot x1 plus b square x1 square, and it should be same thing for x2. So to identically satisfy this, we can already see that delta 1 should be equal to delta 2, then only this is satisfied. So the constraint is identically only satisfied if delta 1 is equal to delta 2. In other, then we can conclude that, in other words, quasi-primary fields are correlated if and only if they have the same scaling dimension, and a 2-point correlator takes the following form. And this discussion can also be done for any statistical field. For example, if the we just replace the action by the free energy functional, and we have translation and rotational invariance as we have for many statistical fields, we can get the 2-point correlation function for them. And as I had described earlier, already has a form of this. This it depends as 2 minus d minus eta. So we can easily see, if we know the scaling dimension of the field, we can calculate the critical exponent eta, and that's a very big thing. Just by imposing symmetry, we can calculate the critical exponent eta, because out of all the critical exponents, all of them are related, and we just only need to know eta and mu, and we already know one of them just by imposing symmetry on the system. So this is just a short example of why conformal field theory is important in physics. So I'm done.
Okay, just a short question before I yield the floor to the others.
Okay.
You said you know the relationship between the critical exponents. Where do you
Yeah.
get know them from? How do you get to know the relationship?
So we under the homogeneity assumption, if we do that, we can get the relationships between the
Okay,
critical
so you have to
exponents.
assume homogeneity for that, or
Yeah, yeah,
at
yeah,
least bring
yeah,
in some kind of renormalization group
yeah,
concerns so that you
yeah,
can get
yeah.
homogeneity.
Yes.
Okay, so anyway, let's have plot first. It was pretty good. Okay, however, I will just warn all of you. Some of you made presentations, some of you wrote it out. It's fine for this course, but for your final presentations in your projects, please take the extra time to make presentations. Okay, if you find, well, if you don't know LaTeX yet or don't know how to create a Beamer slides, ask your friends, they know. That has nothing to do with this course, but I'm just saying that the extra effort that you give to prepare a presentation also counts when people are evaluating your presentations. Okay?
Yes, sir.
I don't mind. This was fine. This actually was pretty well done. I wouldn't dare to do this
Actually, I
simply
was
because my
planning
handwriting
to
is
write.
bad. No, your handwriting is pretty legible and nice, so it actually looks quite good.
I was actually planning to write like you teach in the class, but that thing was not working, so I had to write it down.
Yeah, but what I do in class is also not worth this.
Yeah, you
A
should do
properly prepared
presentation.
presentation is a different thing.
Yeah.
Okay. No, I'm talking about, especially I'm talking about the project presentations. For that, you better put in the effort and make the slides. Okay. So any questions for Ritik? If none, okay, so let me just quickly give you the bad news. The bad news is you will have to take part of the evaluation yourself, which is for the lectures you have heard, each one of you will have to grade the others, including yourself. Uh, I don't want marks. All I want is a relative grading. That is, which one do you think should be number one, number two, number three, and so on. Okay. I want it from all of you. And since life is always unfair, I'm going to assume my own relative grading to be the best. So anybody who comes close to mine will get extra marks. The ones whose gradings are very different from mine are going to get, well, negative marks. That is, I'm going to take away some of the marks I've already decided to award for their lectures. Okay, so this is going to be a small part, but at least let's see whether you can appreciate other people's work as, so the basic idea is how you should grade it not only on how good the content was, how well it was delivered, but also on how well you understood it. Okay. So all of you will have to do this. Send in your gradings. Uh, don't consult each other on this, and you don't have to be modest and grade yours last or anything. Try to be as honest as possible. If you think yours is the best, put it at number one. If you think yours is third best, put it at number three. Okay. So everybody clear about that?
Sir, could you upload these presentations so that
Yeah, I
I
will do that. Do that tomorrow, by
Okay.
tomorrow. But I think you should be able to do it anyway, even without that. That's anyway. I will do that by tomorrow. Okay. So you have to send me the gradings in by next Tuesday, and we are having classes on Tuesday and Thursday, right? Are we? Or
Yes, sir,
you?
that was what was
No, but next
decided
Tuesday,
upon.
Thursday, do you have exams or anything? Was it next week or the week after that? I don't remember.
I don't have any exams as such. I don't know about others.
So let me know if you're free next week. We can actually have classes Tuesday, Wednesday, at least till the end of the month. If we still have exams, then we can start after right after the exams. Tuesday, Thursday, the way we were going before, the same slots. Okay,
I also
thank
don't have
you.
any exams.
And we'll have one more lecture, by the way. Shagor, any idea how he's doing? Okay, Shubhadeep, we were saying something.
I was just saying that I don't have any exams on
So if
next week.
nobody has exams, we can of course go next Tuesday. That is if your exam week is over. Is it? Anyway, let's assume that we are meeting next Tuesday then to finish off, at least finish off the Lie algebra part properly. At least the semi-simple Lie algebra representation part. Okay, bye for now.